We're going to talk about the operational amplifier, or op-amp for short, and this is the workhorse of all analog electronics. And the operational amplifier, it's a type of amplifier. An amplifier is anything that you put an electronic signal in and you get out a larger version of the signal. So this would be an amplifier with some sort of gain, and if I put a signal X in here, usually a voltage or a current, then the signal that comes out here is A times X. And that's what we mean by amplification. And a signal that I've shown here as X is anything that we're interested in. It could be a voltage or a current. And when we put it through an amplifier, we get a larger version of it. So this is a really common activity in electronic design. Now, when we talk specifically about an operational amplifier, the symbol for that we use for an operational amplifier is a triangle. And it has two inputs. One is the plus input, one is the minus input, and it has an output. And it also has two power supplies to it. There's some sort of plus voltage that goes into it, and some sort of minus voltage. So this is the abstract symbol for an op-amp. So when we say the word op-amp, we have some specific properties in mind. One is op-amps have high gain. So in this case, the gain, usually with the symbol A, is something like 10 to the 5th to 10 to the 6th. Really, really high. Another thing we think about when we talk about op-amps is that they're used for feedback circuits. And we'll talk about feedback in the next couple of videos and what that means. But that's the application that we use op-amps for. And the third thing that's distinctive about op-amps is that they have this kind of input. This kind of input here is referred to as a differential input. So an op-amp usually has differential inputs, and that's as opposed to something we call a single-ended input, which would be just one wire. And what a differential input means, it says we can label the voltages here. We'll call this V out, we'll call this V plus, and we'll call this input V minus. And differential input means that V out equals the gain times V plus minus V minus. So the output signal here is proportional to the difference in the voltage between these two signals here. So I want to make a plot of this equation right here, just so we get a good idea of what it looks like. And the axes here are V in and V out, where V in specifically equals V plus minus V minus. V plus minus V minus, that's the input signal to the op-amp, and we're going to apply the gain factor to it to get V out. And so that'll look like this, something like this. It's going to be a very steep line, and the slope of that line, the slope of this line is A. So the slope is going to be 10 to the 5th or 10 to the 6th, something like that, very, very vertical. Now, one of the properties of this is that V out cannot go above or below its power supply voltages. So on this plot here, that's called saturation. If V out gets up to V plus, we say it saturates and looks like this. It goes flat basically here and here, where this voltage value here is minus the power supply, and this voltage right here is the positive power supply. But over this range here, over this range in here, between those 2 points, it's quite linear. It goes through 0, and this is where we use it most of the time. So now I want to talk a little bit more detail about what this symbol means here and what's inside it and how it's actually connected up in a circuit. So we talked about the voltage behavior of an op amp. This is V plus, V minus, and V out. There's one thing more that we need to know, and that is the current. This current right here and this current right here for an op amp, an ideal op amp, is 0. No current flows in here. So this op amp is just sensing the voltages at these points, but no current flows in. So this is the second key property of an op amp. The first one is the voltage behavior. V out equals the gain times V plus minus V minus. Another way we can write this is V out equals A times V in, where V in, of course, equals V plus minus V minus. So these are the two electrical properties that are going to allow us to analyze these circuits. And analyzing the circuits is actually going to be pretty simple. So you're probably wondering, like, what is inside here? What's going on inside here? So what's inside here is somewhere between 20 and 50 or so transistors and resistors, sometimes capacitors. These are really complex designs. And for right now, if we just concentrate on the two properties that we have here, we'll be able to use these circuits even without understanding exactly what's inside. Suffice to say, it's a differential amplifier with really high gain. And with just that knowledge, we can work out how these circuits work. So let me do a couple of more details on how this thing is actually hooked up. So we have a plus terminal and a minus terminal. There's more terminals on this. There's a power supply like this that's plus big V, and there has to be a minus supply, typically a minus supply minus V. And there'll be a ground pin. There'll be a ground node on here, like that. And when this is used in a circuit, there'll be, over to the side, there'll be two power supplies, and this will be 12 volts. 12 volts is a real typical value. And there'll be another one, and this is a plus 12 volt supply as well. And they'll be connected together, and this node right between them will be our ground node. That's the voltage reference. And these two guys will be hooked up like that. The two power supplies will be hooked up this way. So with respect to ground, this node is at minus 12 volts, and this node from ground is at plus 12 volts. And ground is right in the middle. And when we measure V out, we'll measure it with respect to this ground node. So this is the voltage where we measure plus or minus V out right there. And what we're going to do is we're going to assume that all of this stuff is always hooked up, and we're just going to use an even simpler symbol, just the three terminals, like that. And you'll know that all the rest of the power supply is hooked up that way. And the thing to keep in mind is there's a large minus voltage, there's a large plus voltage, and the ground level, the ground node, is right in between. So positive voltage is high on the page, negative voltage is low on the page, and V out can go both positive and negative around ground. So that's your voltage framework to keep in your head. And the op amp that we've been looking at has a symbol like this. And we know that V out equals some huge gain times V plus minus V minus. So this is a differential input. Here's V plus, here's V minus. One way I think about this is to look at the way a change in voltage on the input modifies the output. Let me label V out here. So if there's a change on the input, say V plus goes this way, because it's a plus sign, that means that V out goes this way. Now, if I change it over to V minus is on the negative input. If V minus goes up, then V out goes down. So that's the inverting, it's called the inverting input, and this is called the non-inverting input. So on the non-inverting input, up goes up, And on the inverting input, if you go up on the inverting input, you go in the opposite direction on the output. Let's say that the positive input, the non-inverting input, went down this time. And that means what? That means that V out will go down. And just do the same thing over here. I'm going to run out of colors. Let's do the same thing for the inverting input. If the inverting input goes down, what does the output do? It goes up. It goes in the opposite direction. That's a way to think about this symbol when you see it on a schematic page, is how do these signals translate through the device? Positive non-inverting signals go in the same direction. Inverting signals go in the opposite directions. Okay, and here's one final trick I want to share with you, something to be aware of. You're going to see a symbol like this on a page. The same op amp. It's the same op amp, but it's written on the page with the negative, with the inverting symbol on the top and the non-inverting symbol on the bottom. So as you look at a schematic that has an op amp in it, one of the first things you want to do is just glance and see what order these symbols are in. Or does it look like that, or does it look like that? And keep that in mind as you're reading the circuit and trying to understand what it does. Okay, let's move on and build something with our op amp.